first, I want to start with discuss visual representations. Let's go back to the computer lab where all the action is. Now, code is opaque, so students often draw diagrams to visualize. If you think about the word code, that often means something really cryptic. If I gave you a piece of code like this, if you're familiar with programming, the first thing you're probably going to do unconsciously even is to try to draw a picture of what that code looks like when it's run in your mind's eye. And it turns out students draw this all the time on paper. So you see all pieces of paper all around the computer lab as well as whiteboards. So students use those to try to draw diagrams. In order to facilitate this process, I've created a tool called the Python Tutor that helps students visualize what their code is doing and build proper mental models. So I'm going to play a video demo and narrate over it. You can write code in Python and also in a lot of other languages now. And as you write code on this website, this is from my example from the previous slide, you can hit visualize execution to run your code, and you're brought to this visualization where you can step forward and also backwards, and you can see on the right side a diagram that builds up that shows what's going on at each step of execution when you're running your code. And the design of this tool is trying to emulate an expert walking through code execution step by step. So here, an expert is drawing on the blackboard what happens in a piece of code when it runs. So this Python tutor system tries to emulate these sorts of drawings in a fully automated way online so that you don't need an expert sitting next to you to figure out what's going on. This works not only for Python, but for other popular teaching languages as well. So this is an example in Java. So on the left side, you can see these arrows pointing to step-by-step what's going on in the control flow of the program. So this shows things like if statements, for loops, or function calls. You can see stack frames. So traditionally the stack is drawn growing down. So you can see variables and values in stack frames. And you can also see data structures. In this case, it's a linked list data structure in Java. And again, all of this updates live when you step back and forth throughout the code execution. This is JavaScript, which despite its name is actually very different from Java as a language. This illustrates object-oriented programming concepts in JavaScript. So JavaScript is what's called a prototype-based inheritance language. So this shows the prototype chain. The tool also shows traditional class-based inheritance in languages such as Java, C++, and Python. This is an example from C. So in C and C++, oftentimes what you want to learn are pointer operations. So this shows a character buffer being allocated on the heap and two pointers pointing to the middle of the character buffer. And as execution goes on, those pointers switch locations to illustrate various low-level memory operations. The Python tutor site has gotten quite a lot of usage over the past 8 years. I only have data starting in about mid-2012. I didn't really log the data before that. The y-axis here shows the total pieces of code visualized. Python accounts for by far the most visualizations with almost 50 million. If you add all the other languages on the site, Java, JavaScript, C, C++, and Ruby, which were added about 2 to 3 years ago, you get a few more million. And then if you also add the embeddings, which is the ability to embed Python tutor visualizations into other sites, that brings you well over 50 million pieces of code. And this is all 100% naturalistic growth. There has been zero advertising. I have no ad budget of any sort. There is no company behind this or anything. This is just me running this as an open source project. And a lot of the traffic organically comes not only from search engines, but also from these massive open online courses and other online courses where people are learning programming. And students and also instructors go to my Python tutor site because it's the only place that provides this sort of automated visualization feature. This is a graph showing the total number of unique users. So a safe estimate is around 3.5 million total users over the lifetime of the system. And what excites me more than just sheer number of users is the diversity of the user base around the world. So this map shows that Python tutor has been used pretty much in every country around the world, over 180 countries. And moreover, 60% of the users are over 25 years old. So they're what's called adult learners, and 16%, 1/6, are over 55 years old. And that's what motivated me to do that older adults learning programming study. The majority are non-native English speakers because they come from all over the world. And again, that's what motivated me to do the non-native English speaker study that I presented at the beginning of this talk. The really cool thing about this unique scale is that it allows me to develop and test new systems that bring in-lab interactions to the world. So I want to talk about the first of such systems. So going back to the computer lab, one big observation is that students often work in pairs or small groups, like the pair shown here. The question is, can we bring this interaction outside of lab? To enable this, I've created a multi-user mode on pythontutor.com. So if you start a private chat, you can click a button and send a link to anybody that you know. And when they go to your link, they are brought into a shared session where you can both chat in real time, and then you can visualize code, step through code, and you can see each other's mouse cursors as you move, as though you were both in front of the same computer. And then what other things you can do is that you can also write code together by editing the code and say putting in some print statements, and then run the code again and discuss the visualizations. And the design of the system is trying to emulate 2 or more students sitting side by side working in a computer lab. The research questions here included: can remote pair programming and chat emulate in-lab interactions? Do people chat about visualizations? And can people actually learn and feel a human connection by using this tool? To investigate these questions, I deployed the tool live to the Python Tutor website starting in May 2014. So in the past 4 years, there have been over 4,000 substantive sessions using this tool. So a substantive session I define is one where at least 2 people each sent at least 10 messages or made at least 10 code edits. And the idea here is that there's a bunch of people who are just trying out this tool, playing with it, and just sending some test messages. I really want to count only the sessions where something substantive was going on. So if you sent back and forth at least 10 chat messages, that's a pretty good sign that you're more serious about the session. Also, alternatively, you could make 10 code edits. So there are some sessions that did not seem to have chats, but they had a lot of code edits. And that's because the people actually use the code editor itself to chat, because you can just write text in there as say comments. The substantive chat sessions seem comparable in length to in-person sessions. So this is a distribution of session length, and the median was 37 minutes. So this really is indicative of 2 people or more working together in a lab for a fairly substantial amount of time trying to work through things together. This is not just, someone jumping in for a minute or 2. From analyzing the chat logs, we found out that people interacted like they would in person. So there's roughly a 40-60 split in the data between one-on-one tutoring, where someone was clearly the expert tutoring someone else, and peer-to-peer collaboration, where it was 2 or more students trying to figure some code out together. So here's an example of the one-on-one tutoring case. The tutor says, "Our program crashed. Why do you think it crashed?" And the learner says something, and the tutor says, "What structure is it going to be?" And the tutor says, "Okay, how about sorted T2? How about T1? What's the type? What's the result of adding an integer in a list?" So this is an example of a really good tutor who's using a Socratic questioning method to try to get the learner to isolate their problem. On the other side, here's an example of a peer-to-peer collaboration. So 2 people, A and B, A says, "Oh, I guess base string is checking if it's a string." B says, "You can step forward and backward if you want, perhaps." A says, "Is a string automatically a list in Python?" B, "Let me see." A, no wonder the stack was weird. I guess it calls print items each time we have a string." The thing to note here is that these 2 people are going back and forth, and they're playing with the visualizations and are actually talking about it. Which brings me to the next point, which is that people learn by discussing visualizations. The median for each substantive session was 76 chat messages plus 61 visualization interactions, 61 times where they actually played with the visualization by looking at different parts of execution. And often they were interleaved. So often the chats refer to the visualizations themselves. So example here, there's A and B both pointing to parts of a linked list data structure. And someone says something like, "Reference is deleted, object stays because another reference is still in place. Then a new reference using the same name B is put back in place." So what's indicated by a lot of these quotes is that the students are actually talking about the visualizations. And if the visualizations didn't exist, it would be very hard to make such substantive comments about runtime behavior. The take-home message from this first part of the talk is that visual representations empower discussion. So by creating a Python tutor system that allows people to visualize what their code does under the hood, and then hooking that up with a real-time chat and shared cursor system, that allows people to really have good discussions about what their code is really doing. So an analogy I like to draw is that if you're a beginner, looking at code looks pretty much like this. This code is really obscure, it's cryptic, it's just a bunch of symbols. This code happens to come from the source code of the YouTube homepage, but it might as well just be, some random piece of code to a beginner. So if you are trying to teach a beginner about programming, if all you had to look at was code, it's very hard to have discussions about something really substantive because you don't know really what to talk about beyond just what's the curly braces and the weird letters that are on there. But instead, with a Python tutor system that turns the code into a bunch of images, into a visual representation, and that empowers discussion, just like in the relief sculpture case in the studio, where the instructor and student can both look at a physical visual form and have good discussions about it.